Okay. Good morning, everyone. Uh, oops.
Yep.
Jason, how are you doing? That's
Good, man. How's it going?
um cool. So welcome everyone to this week's AI paper presentation from Tori. Again, where Tori, we handle an hour of work in 5 minutes for hotel sales agents. And if anyone has any media inquiries or requests for internships, let us know, and I'll be happy to put you in touch with our friendly CEO, Jason here, Jason Sincata. So this week's paper presentation is by the CEO of Verinfast, Jason Nichols. Jason, do you want to give a background to yourself at all, or explain what Verinfast works on?
Sure. Um, so background to myself, Julian and I gotta change my background, don't I? There we go. That'll work for now. Julian and I used to work together at Walmart, where I was director of AI for the Intelligent Retail Lab. Before that, I was senior director of innovation for Time Inc. Before that, I was at New York Stock Exchange. Um, I've been working in software development and specifically AI for a long time, almost 20 years now. And yeah, Verinfast is a company that I founded. It's an interesting story. I won't bore you guys with the details, but long story short, I believe there's not enough transparency in the startup ecosystem. I was the CTO of a startup. My founder at the last company was is has now been arrested for wire fraud and has fled the country. And I built Verinfast as a way to verify information fast. It's all right there in the name. So it lets you basically pick out information that you want to share, trusted third-party information that's asserted by either banks, payroll services, source code management, cloud providers, etc. And it produces a normalized view of any company so that investors or even potentially employees can see the report and understand what they're getting into. One of my old employees actually described it as the Carfax for startups. Um, so it's kind of that very quick hit of the facts you need to know asserted without modification by all the third parties who matter.
Very cool. And you have a presentation for today's paper, right?
Yes, sir.
Cool. I'll stop sharing and hand it over to you.
All right. Well, I'm going to apologize in advance. I am not the greatest artist in the world. So for those of you who have suffered through my PowerPoint presentations before, this is going to look very similar. Um, but white screen, black text is basically all you're getting out of me today. And so I actually chose this paper. I really like this paper. I'll give a brief overview of it. Um, the reason for my choice, can everybody still see it?
Yep.
Cool. So twofold. One, I feel like everybody spills a lot of ink on LLMs right now. There's a lot more to AI than LLMs. I'm partial to reinforcement learning. It's always been my bias. Recommender systems are kind of a proto reinforcement learning system. And they're also the one that we probably interact with more than any other form of AI today. And again, further bias, I'm writing my own research paper on the topic. So this happened to be one of the references in my paper. So I had this handy at the time. Brief introduction here. Recommender systems generally have, and I'm going to quote from the paper, that stark structural misalignment. They tend to optimize for short-term signal. That short-term signal is a common problem in all reinforcement learning systems. Optimizing for near-term rewards, these proxy rewards we use to create dense reward functions, often deviates from the actual goal of the system. In this case, a recommender system's true goal is to optimize utility. You want your user to like your service. You don't want them to hate it fast. So optimizing towards engagement just optimizes exactly that. Whereas making bad engagement bad, recommendations that are clicked on are not good. I have a lot of background in this. I used to do search suggestion for IAC. They were the guys who owned ask.com, Ask Jeeves, if you guys are old enough to remember that. But also we've done it at Walmart. We've done it a bunch of places. So in many cases, these kinds of recommender systems are super important. I found the paper to be really confusing to read, to be honest. I felt like they switched back and forth between using the acronym PAIR and DICE, which is very frustrating as I was skimming through the paper the first two times. They are two different algorithms. So I went ahead and did the analysis to break those down. But I felt like the first two times I read this paper, I was like, wait, where did DICE come from? So the always popular policy is basically exactly what it sounds like. Recommend whatever is the most popular. most collaborative filters work like that. They have inevitably evolved to that, even if your attempt is to make it based off similar cohorts. Uh, I say is the subject of the research I'm doing. But specifically, that always popular policy is a good proxy for optimizing for short-term engagement. They had a bunch of good bits here. The dice policy comes from Lattimore, and I'm not even going to get that half right. Sesvari from 2020. If you've worked in multi-arm bandits, that's actually a pretty core piece of literature. We used to use multi-arm bandits extensively at Walmart, specifically for pricing. So again, these are very real-world applications. When they describe niche, I found this to also be frustrating. What they mean by niche here is not just that it has a mean of 0 and a large standard deviation, but they're doing this 2-point distribution. So it's either positive or negative. There's no, let me rephrase this. It can't be very negative or particularly positive. Your utility is not particularly high. It's either going to be that 1 or -1. So then popular, just again, normally in these analyses, popular refers to something with a positive mean and a small standard deviation. They didn't get into a very good definition here, as they said it was chosen with a narrow distribution around a positive mean, which again is close enough to the normal that I didn't worry about it. And then lastly, they introduced that sigma, that discount factor, which I felt they did a poor job explaining as well. If you're not familiar with economics, the sigma discount factor is just how much you weight future reward. So the higher that is, and you'll see this later in the graphs, the more important it is to get to utility. Again, people stop engaging after numerous bad recommendations. So when sigma is 0, the future doesn't matter. They also misspelled GPD, which I noticed in the paper and sent me down a rabbit hole trying to understand what the hell GDP they were talking about was. It is the generalized Pareto distribution. So it is not the gross domestic product, if you were confused by that brief call out here for what GPD is, since again, they don't bother to reference much in the paper here, but effectively on the tail distribution, how much value do you get? That's what they're using the GPD for. So pair, they're posterior-based, exploration-driven, adaptive recommendations. I didn't like the fact that they didn't treat this later in the paper when they did their analysis. They just show it here. Pair does decrease engagement pretty significantly, especially in those cases where that discount factor is low. It doesn't have nearly the negative effect when the discount factor is high, but it does increase utility across all spaces. The reason for this is pretty apparent, and they do the proof later on in the appendix of the paper, but you're going to get the best utility from those things that have the highest utility. So the niches that you like are a +1, whereas all of the populars are going to be less than +1 in terms of utility. So again, it's a pretty straightforward reasoning here, but the risk becomes when you're recommending a niche product that is from the wrong niche, you wind up with a loss. So balancing how often you explore the niche, that high variability area, versus how often you stick to the safe zone, the popular, that really the results depend largely on how much you value the future. So in this case, where sigma is 0, the results are actually pretty negative in terms of engagement. But in this case, where sigma is almost 1, if the future is almost roughly equal to the present, then it actually decreases. I found that result to be unintuitive, personally. I was surprised to see that sigma had such a high impact. It makes sense to a degree, but still, I didn't expect it to be so pronounced. So then just jumping forward into dice, I know I'm going really fast, and I'm going to stop and go back and go over questions in a second, but just so we're all on the same page. The dice algorithm is very simpler. The dice algorithm is not theirs, it's pair. I felt like they should have given more treatment to their algorithm pair when they were comparing here, because we don't get the same kind of graph, which I felt was a letdown. I like pictures. They make it easier to understand. But the picture here is very clear. Under dice, you have a huge improvement with respect to the always popular policy in terms of utility. And now here's where you get into that GPD shape. If the shape parameter, and I think that's epsilon, but my Greek is terrible. If the shape parameter is low, you see no loss in engagement. Whereas if the shape parameter is high, you see a marginal loss of engagement. But this is still being treated with a sigma of like 0.999. I didn't catch that when I copy and pasted this into PowerPoint. So this still has the sigma very near one. The results are not as impressive when the sigma is closer to zero. That's the other red and blue graph in the paper, which I'll show in a second. But yeah, getting to why I thought this was super important, really depending on how much you weight sigma, um, the utility of dice is inarguably and provably substantially higher than the utility of the always popular policy. And again, they get into the proofs later on in the appendix of the paper. But yet, just as sigma approaches one, hey, I don't want to read this out loud because you've got it on the screen in front of you. I feel stupid reading to people, but you see that this is very clearly a remedy to the problem of short-term exploitation in recommender systems. And so again, the reason I brought this up as the paper that I wanted to do today was that I feel like many systems, and Tori specifically, will have recommender systems baked into them at some point. These become critical components of almost any application. And the research here is still ongoing. It's still advancing, and it's still moving towards better recommendations for people because, and again, I'm biased here, but app is crap. There are too many bad recommenders out there that are not delivering utility to users, and stick to that safe zone to maximize that short-term engagement. And that includes everything from feeds we read. I mean, you see this again. It's such a universally applicable algorithm, whether it's in your LinkedIn feed, your X feed, your YouTube recommendations, Netflix, hotel recommendations, and it has a pronounced effect. By having this effect, if you stick to an always popular policy in the hotel space, as an example, you marginalize new businesses as they enter, you reduce the diversity of recommendations. So the effect is riddled throughout the economy, which the authors do talk about a little bit in their introduction. But again, I felt like they could have put a little more into why it's so important to look at the algorithms that you're using for your recommender and why pair and dice. And again, they should have treated pair the same way they treated dice. I feel like the math was harder on pair, but that's still, it's a bit of a cop out. So I wasn't super thrilled with the paper as I was going through it, but the point is they could have treated pair more thoroughly and they could have shown the same results for pair. I think it was equally provable, but they only stuck to dice. But still, there are other algorithms. I don't think pair and dice are the final word. Just going back to them here, they're very, very basic. Incrementing a simple counter is not, right? Like this isn't rocket science here. This is nowhere near as complicated as transformers, but yet it's so broadly applied that, yeah, we could have done this simple change and improved recommendations dramatically, which is, again, going to dice, it's not any more complicated. And dice is the one that's proven. So yeah, that's a 10,000 foot overview of the paper. Is there any part that people want to dive into and discuss, or does anybody have any questions? Anything we want to talk about?
Maybe it would be useful to go over a 101 overview of these two algorithms,
Sure.
people without the context. Yeah.
Yeah. So in your standard recommender system, collaborative filtering, for example, or sympathetic filtering, I forget what they call it now. In your standard recommender system, you basically have a matrix of people and products. And for every user that has rated the product, you record either a +1 or a -1. And then in an always popular, you just take the one with the highest score, right? You just take the column for the product with that highest score. And you don't really get a good personalization. Modern personalization will attempt to do something where they look for a person who is like you. So think of it as a like a Manhattan distance, basically. So you have a vector, which is your row, so all the +1s and -1s, and you try to see how many are similar, right? So again, it's kind of a modified Manhattan distance. You want to say, okay, I'm going to find all the people who are closest to me, and then I'm going to pick the product that they've recommended that is the most popular. So it still winds up becoming very similar to an always popular recommender. Again, biased here because that's my research. But the point is that they're comparing always popular because the de facto assumption is that's going to be the baseline. Here, what they're saying is, okay, take one of those popular items. So in this case, we're going to recommend the diverse items to the posterior at least P. So basically, we're going to believe that you should get diverse items instead of popular items until we're proven wrong. So as long as your counter is less, so P here, right? We've initialized it. We're going to update it here, right, for the next P. As long as that posterior stays above this threshold, we're going to go ahead and continue to recommend diverse recommendations. Otherwise, we'll recommend only popular recommendations. So the key is that it's kind of a binary, right? You're getting either niche recommendations, which are classified as having that highly polar 2-point distribution, or you're getting popular recommendations, which are classified as having that very narrow, small standard deviation, but lower, technically higher median distribution, right? The idea is that the mean of a popular is going to be positive, but the standard deviation is small, whereas the mean of a niche is 0, but the standard deviation is large. So in this case, you're just incrementing your success and failure counter, and then for each subsequent time tick, t+1 for the next iteration, you're updating your posterior belief. So it's kind of Bayesian reasoning about whether or not you should get niche or popular. Whereas for this guy, so you're going to get your diverse recommendations. And then you're going to get your popular recommendations. And if the user chooses more of the popular, if they have that preference for popular, then you're going to make sure that you're going to include an additional recommendation based on popular or niche. So effectively what this one is doing is that you wind up with a gradient as opposed to a binary, right? You could get 2 popular, you could get 2 niche, you could get 1 popular, 1 niche. It's not quite the same, and the probability distribution is smoother as opposed to having a cutoff.
Yeah.
So in this case, because of that smoother transition, you don't see the misalignments with engagement because you're not guaranteed to get only niche. You're not guaranteed to get only popular. And you don't get like bucketed back and forth. This one has more of an ability to pull you back toward niche or up towards popular again, as opposed to pair. Basically, once you cross that threshold, you're only getting popular recommendations, which means you'll only ever get popular recommendations again.
Yeah.
So pair kind of dips you in and explores first. Pair is very similar to like the multi-arm bandit strategy of explore then exploit, except the problem with pair that Dice addresses is that you don't ever come back, right? There's no way to shift back down to niche. You just wind up in popular. So pair approximates app in as time goes to infinity, because eventually everybody will have picked enough populars to modify the distribution function to move them out of niche. Does that help put some context around these?
Yeah, I've had conversations around this, maybe without knowing the names of these algorithms before. So you have, TikTok as an example, and you start with a cold start problem where you need to say get an embedding for users or just understand what content they want to see. But as you're noting, you don't want to just only show them the popular content. So I think part of the discussion I had before is you can potentially show them like a diversified array of items, and that gives you a better, you can zoom in faster on what they actually would like to see, as opposed to only showing them like the top 10 most popular items.
That's the philosophy behind pair, is that start with that diversified base, and only once you reach a critical threshold, then you're showing them only popular.
Jason, how do they run the math? Is this just what they're showing down there in that table on the right? That's how you select kind of what an ideal basis point is for that turning point?
Yeah, so the problem is they don't do the proof for the math for pair, which again is kind of my gripe here. So yeah, that is basically it. There isn't anything in the appendix on pair to say what the ideal P is.
Yeah, yeah.
So you have P0, like, but there isn't anything that tells me, okay, you show me how to initialize, but there isn't anything that tells me where P should be changed. It's just, that's the problem. So effectively, this P is the same P that's used in the here, the niche probability. So if the niche probability is such that niche items, it is very uncommon for niche items to have a positive utility, then that P is low. If it's very common for them to have positive utility, then that P is higher. But like they don't prove, they just run this with this discount factor. They don't, it's just simulation. So. I hate that this is cutting off your name. I'm sorry, I don't know who that was talking, but I can't get Zoom to be larger.
Oh, sorry. Oh, Madison over here.
Madison. Any other questions? I know I went really fast. I tend to talk really fast. I'm sorry about that.
Yeah, Jason, how is utility calculated in this paper?
So utility is not calculated. It is given as a given. So in the case of the niche items, it's given here. So your probability distribution function is in the paper. And then for the popular items, they don't actually give the calculation. They just show that it's positive and with a low variation.
Yep.
So the assumption is that for niche items, they have that 2-point distribution. Here, let me see if I can pull up the paper itself. There we go. It's a lot more legible there. But yeah, you're either getting, in the case of P equals 0.5, where does they say it right here? It's the 2-point distribution. Oh, where did it go? And they say it somewhere in the paper where utility is either -1 or +1.
Got it. Yeah, thanks.
No worries. But yeah, that probability is what gets it to be a mean of 0, because a certain amount of the time it's over, a certain amount it's under. And
I'm assuming that these algorithms are more the mathematical basis of things, so it doesn't really matter whether you're doing like a 2-tower model versus collaborative filtering, or does it?
It does matter. So, and again, this is where I'm going off the reservation here, because I'm talking about my ownership. In theory, these recommender systems like collaborative filtering are designed to counter the known flaw in app, but in practice, many of them lack a theoretical proof to demonstrate the impact, and many of them have parameters that enable tweaking, like dice and like pair have that discount factor, and the changing of those parameters meaningfully impacts. So scrolling down here, right, I didn't include this image in the graph, but with that sigma of 0, dice don't look so good, right? Like it's a meaningful decrease here. There's much more decrease in both utility and engagement. So the point is, yes, it matters. It matters very deeply how these systems are configured. The general principles don't change, right? There is a self-reinforcing nature of popularity that will never change. If you show 1 million people the same TikTok video, it's going to have more likes than one that's not been shown to anyone, because that's just, there's no way around. You know what I mean? Like, and then there becomes a self-reinforcing nature where if people share at least some basic similarities, there's going to be a probability, a mean for popular videos that is non-zero, which is the assumption here for utility. And so over a large enough time horizon, whatever feedback signal you get becomes infinite, right? If the expected rating is positive, then an infinite number of positives, no matter how infinitesimal, will sum to infinity.
Yeah.
Yeah, it's interesting. It seems like the only way to really test the success of this would be empirically, basically by running some kind of A/B test with different strategies. But then, like you're saying, there's it it's it's really weird as an experiment because the algorithm is like changing what content gets shown, so it winds up being, part of the whole equation. It becomes like very I understand why they're doing this in simulation, basically, because otherwise it becomes very hard to actually reproduce results, probably. But I think this is super interesting. Like if you're starting from scratch and you have a bunch of content and no data, that's I mean, yeah, this is a really interesting approach. I actually worked on a recommender system at my old job, but it was basically the opposite problem, where we had a ton of data and the frequency was like very low. So we would run like a massive batch process once a month. And actually there the solution, obviously it's like completely different. So what we wound up doing was using actually a linear regression to predict, whatever the utility was. For us it was like dollars spent. And then we would take kind of like a relative ranking of everyone. So we had 100 million people that we were ranking, and then basically if you had a really high score across, everything, we would kind of discount, like, because some people are just very high spenders, right? Like some people will just spend a long time on TikTok scrolling through every video. So you kind of discount it. So it's like if they're really, really high everywhere, you take the point where they're the highest. And same with where if they're really, really low everywhere. So we wound up coming up with this system, and it wound up being pretty simple, and it wound up being pretty effective. But it was obviously like a completely different context. So this is like, it's interesting to hear about how people are solving like these other problems that are, like the cold start is yeah, I haven't had to think about that.
Well, that's it. The algorithms are, to your point, inherently simple. It's just that small choices of initial starting parameters wind up creating profound effects because of the self-reinforcing nature, where it's like, oh yeah, whatever it is I chose to recommend makes it look like I did a good job because I chose to recommend it, so it got more engagement. So my recommender system must be good. And this faulty logic of, yeah, but was it optimal? And it's only when you're doing like these kind of, in the paper I'm writing, I joke with the guy that I'm working with that we call it like the God mode view, where I know what utility is for each pairing of person and good because we've already created that matrix, and that's hard code. Like we know that to start with, but seeing where we deviate from optimal utility is impossible in practice because there's a host of economic problems that make that impossible, not least of which is people suck at communicating. So if you were to ask them to like stack rank or score or anything, first off, they'd have to have consumed all of the goods. Secondly, they'd have to have perfect memory. Thirdly, they'd have to be able to like consistently reproduce those rankings, which we know they can't. So outside of simulation, any of this research is very challenging in the field because it's, yeah, humans are squishy and they don't follow instructions. So it's like it's a very interesting mathematical problem, but I love this problem space because it's one of the few areas where within a few hours you can immediately understand the algorithm, but you could then spend the rest of your career understanding the implications of tweaking even small aspects. Like people take for granted in the research I'm working on now, the cost budget of preview. If it takes me 1 second to look, or if it takes me 10 seconds to look, or 100 seconds to evaluate a recommendation, that budget comes out of my consumption budget. So in the case of like Netflix for movie recommendation, if I'm scrolling up TikTok, I may only have 2 free hours to kill. And if it takes me an hour to find a movie I like, then I don't consume any movie that night. You know what I mean? So there's even that level of reinforcement of, if people are choosy and have a higher expected and this goes for like high priced goods as well, then they're willing to do more research. You see that in consumer behavior around cars and houses as opposed to, let's say fruit, right? People will walk into the market and just pick up a banana and go. That's fine, but they very rarely do that with a Bentley, right? So when there's a high cost of consumption, then a greater budget is allocated to research. But if there's a higher cost of evaluation, then even still fewer options are researched. So if it goes and you have to spend, in the case of what Verinfast does, for example, when private equity firms are looking to buy companies, diligence costs many tens to hundreds of thousands, in some cases millions of dollars. So you don't do a deep diligence on an infinite number of companies. So you have to be very choosy in who your recommender stream is. So again, my point is that this is just such a universally applicable problem space that I've always particularly found it fascinating, personally.
Could it be argued though that the reward function, if maybe this is too unrealistic, but if the reward function is perfect, wouldn't it capture these long-term effects? Just kind of like by itself.
If the reward function were perfect, yes. But the point is, as we're unable to measure the reward due to an information
Here would
blocker.
be, the financial performance of the company. It would be the amount of views over time. It'd be the
right, but you don't know that a priori.
Yeah.
So if the reward
But you
function
have theoretically past training data, maybe, right? And you would be able to train off that and see. Well, I guess you would need a lot of experiments conducted, over time.
right, that's you get to, okay, what level of collaborative filtering am I targeting? How, do I build a custom classifier, do linear regression? How do I get to a point where I can predict the utility for this person? And then
I think maybe that's part of what I'm thinking is I'm thinking of this as like a reinforcement learning problem, not just like a collaborative filtering problem. Sorry.
Collaborative filtering is reinforcement learning. By definition, any feedback goes into the system, the matrix is updated, the recommendations change. That's my point.
But maybe I'm missing, where's the exploration part of the collaborative filtering?
So under collaborative filtering, traditionally the cold start problem is solved simply by doing random choice.
Yeah.
You randomly weight the equally similar profiles, since all profiles are equally similar in the initial state because they all have zero data. You just randomly choose a good.
Yeah. Over time, I think I'm imagining, there's still some level of random, not random, but selective, using Bayesian probabilities, exploration taking place.
But I mean, that's what Pair is doing.
Okay, yeah.
Yeah, it's stochastic gradient descent, right? Is basically like randomly updating weights, kind of like this is doing. But what I was gonna say is I took a nonlinear dynamics and chaos course in college, and there you kind of talk about like the butterfly effect kind of thing. And I think that's like where my mind is going, talking about all of this, where basically, like the choices that you make now will influence the future in ways that are like very, very well, it's interesting because if you actually have a good enough model of the system, you can look at the initial parameters and then you can actually map out equilibrium points in the system. So like the classic example is, like, this isn't a chaotic example, but like with a pendulum, right? You can have different states. You can have it just be completely like flat, but then you have the, like it's just going back and forth, and that's like where you approximate it as a sine wave. But then you also have these other points that are not usually considered when you model the system, right? Which is the pendulum is actually balanced completely upside down. And that is a stable point. It's like stable at one very specific point. As soon as you move it, it becomes unstable. And then the other model is actually, it's rotating around completely, right? And so all depending on the initial parameters of the system, you wind up with different outcomes of like how the pendulum moves. And so, yeah, there's ways of like mapping this
attractors.
It's complicated, yeah.
So those are attractor points in the system. And that's one of the points of the research I'm doing is that the app model becomes an attractor for all systems, because based on what you choose. So if you randomly pair, let's just stick with movies and people, right? If you randomly pair a movie to a person, and it's a niche movie, in this case, that they by 2-point distribution.
Mhm.
If you have a high enough probability that that person is not in that niche, then there's a high probability that that movie's initial weight is negative. Its first rating is negative,
Yep.
which means that it'll never be recommended to anyone else again
Mhm.
because all of its weights are negative, right? It's getting a
Mhm.
negative popularity, even amongst people who aren't like you, but it's never getting shown to people who are like you, so you would be in that niche.
Mhm.
Because by definition, if the majority of people are not in the niche, when they're the cold start that Julian brought up, when that random cold start happens and it's first shown to someone by chance, then there's a high chance they got negative utility, even if you would have gotten a higher utility from it personally,
Mhm.
because it's in your niche, right? Like it
Mhm.
really varies wildly based on who those initial pairings are from viewer to
Yeah.
movie, or and again, it doesn't matter if it's viewer to movie, but whomever, those
Yeah.
initial pairings set that initial state,
Yeah.
and then that initial state eventually, again, in my research I'm working on, always attracts to its stable configuration of app, which is
Yeah.
always suboptimal.
Mm. Yeah, it almost, I don't know how, but like in my mind, what another thing that's popping up is like almost like optimal stopping theorem, where it's
Mhm.
like, where do you, just give up, like because maybe you show to fix that problem, you show the movie again and again and again, but at a certain point, you gotta say like, all right, this isn't worth it. So what is
Nobody likes this movie.
threshold?
Yeah.
Yeah,
Like
yeah,
100 times. Well, that's it. There's
yeah.
all of these factors that go in of how deep do you go on exploration? Is
Mhm.
there an additional exploration factor per good, or is it only per person? So
Mhm.
pair and dice only consider the individual receiving the recommendation. They don't consider the item being recommended. So in
Mm.
those cases,
Oh,
like, do you want to make sure you have a statistically significant sample of people who have reviewed this movie?
mhm.
Where is optimal stopping as you approach an infinite number of negative reviews? You can say that the probability that the next review will be negative approaches one,
Yeah.
but like, what does that curve look like, and how does your initial choice of measurement
Mhm.
affect that? Because if you just chose a bunch of people who are like really hate movies, right, to your point, you
Yeah.
have to look at the individual's overall ratings.
Mhm.
If somebody has a mean rating that's low, that's negative, right, they always thumbs down movies, then some thumbs down from them probably means less signal than
Mhm.
somebody who has a mean rating that's high.
Mhm.
But like those kinds of interactions and crosswise interactions, they're ignored in almost any recommender system because they're really hard to model,
Yeah.
and they are totally chaotic as you evolve the system. That one initial input or those first 10 inputs or 100 inputs shape everything going forward.
Mhm. Yeah, yeah, I guess, yeah, when the state space, right, of the problem is like so large. So yeah, I guess it becomes impossible to actually, I mean, I don't know, maybe not impossible, but it becomes conceptually difficult to think about like a lot of the chaos, like problems that we wound up actually analyzing in chaos theory. Your state space is like 4 or 5 variables, so you
Right.
can actually like draw, like it's kind of beautiful. You can draw out how it works based on the initial parameters, right? But yeah, with something like this, it's like you can't think in a million dimensions. So
Right. If you have a
yeah.
matrix of like just taking Netflix as the classic recommender or Spotify, right?
Hmm.
Your matrix, while only two-dimensional, is
Hmm.
functionally infinite, right? Like there's probably nearly a billion users, so there's nearly a billion rows on Spotify.
Hmm.
And then the number of songs and podcasts is, I would guess, in the tens of millions, if not hundreds.
Hmm.
So your state space just for Spotify
Hmm.
quickly becomes many orders of magnitude larger than the population, the human population.
Yeah, 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 yeah.
And it's like every one of those has 3 states,
Hmm.
right? So now it's 3 to the whatever, 3 to the 10 to the 20th or whatever.
Yeah, yeah.
It's a very challenging world to modify, because understanding, to your point, like which states create attractors, which sets of rules create attractors to force a system to coalesce into which repeating, it's like Conway's game of life, right? You have
Hmm.
these variations that just appear, and this order that comes out of simple rules. It's an emergent property,
Hmm.
but
Hmm.
it does look like, and again, I throw my own paper out here, which I haven't even put on archive yet, so it's like 6 months away. But
Hmm.
it does look like, from my research, that they all eventually will converge to an app. But, yeah, they're always popular. Which, yeah, has it, like I said, they then just even thinking about from an ethics standpoint, what does that mean, right? If every recommender system will have a deleterious effect on economic competition because new goods by definition are less popular than established, like that's seems like a problematic thing someone should look at. Which again was kind of the choice they chose here. They went after the fault in our stars, but the fault in our recommendations, like the perils really are there, right? If you optimize easy measure, what does this mean for society as a whole? So I think that's important. And because they're on Amazon, they're on Spotify, they're on Netflix, they shape the goods, the businesses, the consumers, the media, the political landscape. And nobody ever stops to think, man, like, what does this actually do? Like, how does this thing that shows what article I should read next on CNN, right? Outbrain has this super advanced algorithm that they're using for internal and external recommendations to optimize clicks, right? And I came from Time as the senior director of innovation, so very familiar with that one, right? There's one there. There's one on Amazon that says, what product should I buy? There's one on Google that says, what are my search results? It's just a recommender system, right? It's taking the space of all websites, doing a similarity metric, but then also using a popularity metric or some other engagement. They openly talk about that as part of the weight. And it's like, damn, dude, that starts to look like my entire universe of what I read, what I listen to, what I buy, what I watch, where I go, what restaurants get recommended to me, are all being controlled by this relatively primitive algorithm, but with this chaotic, to your point, like unpredictable behavior. And I think we should spend a little more time researching it, as my biased, not humble opinion at all.
Yeah, no, I think, I guess it's to your point of like, you measure what's easy to measure, right? And it's like, somehow there is probably a way to capture more of a fairness, like to optimize for fairness somehow, and add a little bit of more complexity to the metrics, and maybe even the same algorithms would actually work, but getting the buy-in and making a case that I guess, like at the end of the day, right, what's good, like utility, the fact that utility is a given, right, that's like the biggest problem, because that's just like clearly not true among humans. Of it's like we can't agree on what's good and what's bad, and so it's, man, it's a quagmire.
It is. It's a truly like daunting challenge. So, and the other point, like we talk about it in business, but like in management, whatever you measure, people begin to optimize for. And so, there's that further aspect of the system, which is the goods evolve over time, but the people also evolve over time. So the relationship changes over time. But like, we all know what clickbait search results look like today. And so we try to kick past them as quickly as we can. But like those clickbait search results are the result of an industry of optimization, right? Search engine optimization, specifically optimizing content for a recommender system. So, it's that temporal evolution, which means the next tick could be so significantly different in the interactions of goods and people and presentation and choice and selection from the first tick, that those rules that we crafted in that first tick when we launched the system are just garbage now, which is why Google has to update their algorithm every 1 to 5 years, depending on how fast SEO goes.
Going back to my point a little bit, I feel like there could be more signals into the reward function that help with this problem. So like, let's say just users were able to say this content, even though I clicked on it and wrote like hate message back, I didn't, it didn't add to my enjoyment over the course of the day. I'd like to see it less. I feel like that would create recommendations that aren't just maximizing for say views or click through.
So you can use signal like that, and collaborative filtering will often use this +1, -1, thumbs up, thumbs down signal. And the research I'm doing is actually specifically on those signals as lossy compression of true utility.
Yeah,
Because the reality is, I don't enjoy things 1 unit of utility or disenjoy them 1 unit of utility. Some things get a +1 that I fucking love that are a +10, but by only compressing my options to, the +1, -1, or the star rating system, or any small space of utility, you necessarily have a lossy compression. And so that whatever proxy you use is necessarily imperfect, because there'll always be that loss where I can't effectively communicate the difference between a 2.1 star and a 2.5 star dinner. And the chances are, if I'm rating the thing, then you have the polarity behavior of humans, where anything below 2.5, I'm probably going to give a 1 star to, right? Like that's just the nature of how humans behave. We see this in Amazon ratings. The high polarity 1s and 5s and nothing in the middle. But you also see that change over time, right? So Amazon ratings were highly polar, and they became less and less so over time as consumers got more nuanced in their ratings. But Uber ratings are still 5 or 1, and Uber ratings are notoriously 99.999% 5s, and drivers get axed at like a 4.9, because it's so infrequent that you get 1s that like, man, you must be really out there screwing up. So there is a huge problem in the communication channel where the experienced utility isn't adequately captured by the system, because the system's granularity of capture is so small relative to the diversity of utility. Yeah, just think of it, if there's like a continuous utility function from -1 to +1, where -1 is you just freaking die right there, right? It's the worst experience. And +1 is like absolute perfection of experience. Even still, by giving me any finite level of response, you're necessarily compressing that space and mapping it into a lossy compression function, where two things that could be ordered in the first space can no longer be ordered in the second space.
Yeah, that's interesting. This reminds me a little bit. I was working with basically like how much people had paid. That was the utility, I guess you could call it. And there was not, obviously we have, it's somewhat similar because different different places will have discrete values, and then you can buy different items, so it sums up to like there's obviously more variety than from 0 to 5 stars. But one of the interesting things is that you can't spend less than 0 at a place. And so there's, how do you model people's spend? And so there's this like idea of like censoring. Basically there's this idea of, like imagine people could actually take money from the store and spend negative money there if they wanted to, and then build a regression that way, and then all the negative values just convert them to 0, because you can't actually do that in real life. So there's I think that is like a problem I've run into in another context. But yeah, it's hard to measure. Like I think with a discrete 5-star thing, like it would be very, very hard to get like actual strong signal out of that, like you're saying.
Right, and spend is also mediated by budget. So no one spends infinite money either. You can't spend negative. You can't spend, really practically speaking, probably more than a few thousand. But like, would you if you could? And that's why spend as a proxy for utility, or anything as a proxy for utility, is always challenging, because two people might have bought the most expensive item in the restaurant, and one of them would have paid 10 times more, but like that wasn't the price, right? That's the granular price at that point is what it is. So you're still not capturing, and it's any arbitrary, and this is a provable result, right? This is Condorcet, this is Arrow, right? Preference can't be modeled into discrete choices if it's a continuous preference. And so it doesn't matter how granular you make it, was my point of, at the very least, it's engagement, which is 0 or 1. Better still is, thumbs up, thumbs down. So you get -1, 0, 1. Better still is 0 to 5 stars, or 1 to 5 stars, or something along that line. Better still is price, it is payment, or is some numerical value that's, preferably unbounded, but in your case, bounded. But all of those values will always suffer as the underlying data structure by definition is finite and discrete, right? You cannot store a continuous value. This FP32, FP64, we only got so many bytes here, right? That's it. So by definition, you're always going to have a bucketing problem. And so the question is, if you always have a bucketing problem, does the bucketing problem always produce the same result? And again, this is the question for my stuff, not for theirs. But does the bucketing problem always produce the same result? And if it does, again, then what is the implication of that? But no, I'm with you, Julian, that engagement is the worst, the absolute worst proxy metric. Ratings are better, spend is better, everything is better than engagement. But they all suffer the same failure eventually.
Awesome. Any last questions before we wrap up? Niati, what was your favorite part of the presentation?
Just learning these new terms. I have not really looked into this, so like I'm not really looked into recommender systems at all. So yeah. Hey Jason.
Hey, Niati, I didn't even realize you're on.
Yeah, Julian just sent me the link, so I was like, let me obviously join.
Well, I'm sorry you had to listen to me babble for an hour. You put up with that for like a year and a half.
I can put up some more, don't worry.
Thank you.
Okay, awesome. Cool. Well, we look forward to Jason's actual paper when it comes out. In 6
God willing. Yeah,
Or-
exactly. I got to get the time to work on this in between selling my company. So
Awesome. So I'll just give a lead in to Jisong's paper next week. Yeah, Jisong, do you want to give a quick summary of what you'll be talking about, if you'd like to, or we can wait until next week?
I can briefly introduce like the paper. I think it's not my paper, but it's the paper like published from Pinterest that we're gonna walk through. And this paper describes how to leverage the user activity, the user history, could translate to user sequence, and how to use transformer to encode all these things and feed into our recommendation system, especially the ranking system, such that we boost a lot user engagement metrics.
Yeah, fantastic.
And I would say it's very practical things because it's actually come from the real project we're working on, and then we translate to the paper one. So it won't be very academic, but it definitely have some academic aspect, but it's more focused on the industry practice. Yeah, so stay tuned for that.
Very exciting. Yeah, great. Yeah, great segue there. Okay, yeah. Yeah, excited for that paper, and just have a great week, everyone.
Yeah, bye.
thank you, everyone.
Thanks, everyone.